Okay, functions. Functions. F from A to B. Okay, as discussed last time, we have two related definitions for a function, and actually one is slightly more broad than the other. So our first definition is an assignment. So a function is an assignment to each element of A, a unique element of B. Okay, that's a reasonable way to define functions that makes sense with our current intuition. But because we're going to be very particular about definitions and about logic, what we're also going to use is this definition. A function is also a relation R, which is a subset of A cross B, such that for all A in A, there exists a unique tuple, right? Because a subset of A cross B, well, this is a set of tuples. So I'm saying there exists a unique tuple A comma B in R, in the relation, which is a subset of A cross B. Okay, so the thing that, oh, let me focus. Hopefully this is clear. How's the writing looking? Haven't gotten any complaints, so. All right, cool. So what does definition 2 afford us? Definition 2 affords us the empty function. So I claim there exists some function, which I'll call f, from the empty set to B, where B is any non-empty set. So there exists f from the empty set to B, and actually there exists a unique empty function. Okay. Definition 1 of a function doesn't really help us with understanding what this function could possibly be, but definition 2 does help us. So definition 2 says that I should look for a relation on A cross B, or in other words, or a relation from A to B, or in other words, a subset of A cross B. So what is the empty set cross B, where B is an arbitrary set? What is this set?
Is that the empty set?
Yeah, this is the empty set, right? Because this collection here is the collection of all tuples where A lives inside the first set and B lives inside the second set, but the first set has no elements, so there can't be any tuples. So this is the empty set. Okay, what are subsets of the empty set? What are subsets of the empty set?
It's just the empty set, right?
That's right. There's a unique subset of the empty set, and that is the empty set. The empty set is the unique subset of the empty set. Okay, so the only possible relation on the empty set cross B is the empty set. But the empty set is indeed a relation on the empty set cross B because it's the empty set. Okay, and now we must check the condition. So the things that we needed for a function are we needed a relation, or in other words, a subset of A cross B, such that for all A in A, this holds. And this is an if-then sort of thing. So we need whenever an A exists in A, that must imply that this thing holds true. However, are there any elements A in A? If A is the empty set? No, that's right. This condition is always false. So if we break this statement down, for all A in A, this should imply there exists a unique A, B in R. Well, really, maybe I should write it the following way. For all X in A implies there exists a unique tuple X comma B in R. But as Oscar has pointed out, there are no X's in A when A is the empty set. So this statement, for all X inside the empty set implies there exists a unique X comma B in R. Since the premise of the implication is false, that means the entire implication is what?
True.
It's true. So this is vacuously true. In other words, the subset of, or the relation from the empty set to B given by the empty set also satisfies this condition that for all A in A, there exists a unique tuple A, B in the relation vacuously. This extra condition is vacuously satisfied if I pick the subset of the empty set called the empty set. So there's a unique function from the empty set to any B. And this is kind of difficult to wrap your head around. Well, we do know what it is. We know what it is because what is the definition of a function? It is at its core a relation with some extra conditions. And I have picked out for you the only possible relation. So if you transition, like I know that we're going to think of functions as mapping elements of the first set to the second set, but I want you to kind of shift your perspective for a moment and say, every time that we can do that, we could also define that with a relation. And now we pick up this extra boundary case where can you name a relation from the empty set to set B? And since this is the empty set, there exists a unique relation from the empty set to beta or to B, and it's just the empty set. So I know precisely what it is. It's just, it doesn't make sense when you think of it in terms of assigning elements to A to elements of B. Does that kind of help? Right. Like for all the other functions that we're going to be doing, like here's a function A, B, C, here are 3 points, and here are 2 points, 1 and 2. Okay, here's a function. A gets sent to 1, B gets sent to 2, and C gets sent to 1. So on the set A, B, C cross 1, 2, the way that we think about this function f is it's given by the set of tuples A1, B2, and C1, right? So this is a subset of this thing, right? A1, A comma 1, B comma 2, C comma 1 is indeed a subset of this Cartesian product. Here, for the empty set cross beta, this is equal to the empty set, and the only subset of the empty set is just the empty set. So it makes sense to call this the function because we check that it satisfies this extra condition vacuously. That's kind of all that we can say. It's a relation that satisfies a condition. Probably you all already understood that. That is an excellent question. that is actually the next thing that I was going to discuss. Let's say A is not the empty set. Okay. Does there exist a G from A to the empty set? And this is a good question. What do you all think? Everybody raise your hands if you think there exists such a function. Not getting very many hand raises. Can someone tell me why they feel there is not such a function? Ah, Naomi?
I think that's a very complicated question because isn't one of the empty set, well, an empty set is part of A, so wouldn't that be an element for which the function is true?
Well,
Or is
the
that not how
empty
that
set
works?
is a subset of A, but it's not an element of A. So here comes that distinction again. So if we want to find a function from A to the empty set, the first thing that we need to do is we need to find a relation from A to the empty set. So what is a relation? A relation from A to the empty set is a subset of A cross the empty set, right?
Yes.
What is any set cross the empty set?
The empty set.
Right. But A cross the empty set is equal to the empty set. And what is the only subset of the empty set?
An empty set.
Right. The only subset is the empty set. Now what I need to do is go back and check that this relation satisfies this additional condition. For all A and A, I need there to exist a tuple inside the cross product. But
Okay.
now this isn't vacuously true because I assumed A was not empty, right? A is some actual set, so there are actual elements that I can play with here, but no tuples of the form A comma B exist inside this subset, the empty set. For instance, if let's see, let's do this with an actual example. Let's try to think about a possible function from the set 1, 2, 3. So A is equal to the set 1, 2, 3. And A cross the empty set is the empty set, with the only subset being the empty set. And now what I need is for all X, if X is in A, that should imply there exists a unique tuple A comma B inside the relation. But here the relation is just the empty set. Is this implication ever true? Or is this implication ever false? Because the moment that it's false, then this statement isn't true.
So the statement is saying there needs to be an element inside of A that implies that there is a unique tuple inside of the empty set.
Exactly, but there are no tuples inside the empty set. So for instance, I pick a 1 inside A, because 1 is an element of A, right?
Yes.
But there are no tuples of the form 1 comma B. 1 comma B is not a tuple that lives inside the empty set because nothing lives inside the empty set.
So why is this one not vacuously true, but the other one was?
So this one is vacuously true. So remember, if we have a statement P implies Q, if P is always false, then P implies Q is true, right? And that's exactly what we had over here, because when we're mapping from the empty set, the condition that, or the proposition that there exists an element of the first set is always false, right? Exists an element in A implies there exists a unique pair A, B in the relation. Well, when A is the empty set, there's never an element inside the empty set, so this is always false.
Oh, okay. But in the second example, there are things in the empty
Exactly.
set.
There are elements inside the set A, so P is sometimes true. And then I have to check for all those cases when P is true, I have to make sure that Q is true as well. But for 1 in A, there is no tuple 1 comma B inside the empty set, so P is true, but Q is false.
Oh,
There
okay.
does not exist a tuple 1 comma anything inside the empty set.
Meaning that the whole thing is false,
whole thing is
meaning that there's not a
false.
function, right?
Exactly. So
Oh.
this subset, the empty set, is not a function from A to the empty set because it doesn't satisfy that condition.
We love learning.
Yeah, so this is a great example of some of the tricky things that we have to think about and be able to accept and deal with when we're dealing with a logical system and we're dealing with definitions like this. So these concepts of the empty function from the empty set to a set, or there not being a function from A to the empty set, are interesting, but they're kind of different from our usual understanding of functions, right? So I'm going to do some more standard examples, but before I get to any more standard examples, does anyone have any further questions about these empty functions or the non-existence of functions to the empty set?
I have a quick question again.
Sure, yeah.
So for the empty set, it doesn't have any elements, but the subset of the empty set is the empty set. Is that correct?
Yes, so the empty set contains no elements, but there does exist a unique subset of the empty set, which is the empty set.
Okay. Just wanted to make sure for my notes.
Yep.
So if both A and B are the empty set, it would still just be like an empty function, like when A is the empty set, right?
That's right. I can define, and this is particularly perverse. I can define a function from the empty set to the empty set. This works because in this case, the relation, the empty set, contained as a subset of the empty set cross the empty set, does satisfy all the properties. So this works out. I can define an empty function from the empty set to the empty set, but this only works when the first term is the empty set. The moment that I have something non-empty in the first place, then it breaks for the reason above. Is that okay?
Yes, thank you.
Yeah, so this works. But the moment that the domain is non-empty, then you don't have a function from a non-empty set to the empty set. Okay. Let me first give some nomenclature. Usually I'll write f from A to B. This denotes a function from A to B, and then I'll either write A maps to B to tell you that the function sends the element A to B, or I'll write f of, or B is equal to f of A. Both of these are ways of telling you what the tuple is. In the relation language, this is going to be called like A comma f of A or A comma B. These are all ways of describing the possible tuples that we have given by the function f from A to B. This is called the domain. The first set is called the domain. The set B is called the codomain. And the collection, the set, well, the image of f, which I can write mf, the image of f, is equal to the collection of all b in B such that there exists an A in A and f of A is equal to B. This is also called the range. B here is called the image of A. B is the image of A, and A is A preimage of B. Okay, lot of terminology, but hopefully this is okay because y'all read it. Let's do a basic example. Let's deal with something like this. Let's give me some animals, like a lizard and a seagull.
Squirrel.
Squirrel, thank you. One more animal, please. Tiger. Great, so now I have a domain set which consists of a lizard, seagull, a squirrel, and a tiger. And then here we're going to list their ferocity on a scale of 1 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Please list, so what is the ferocity of a lizard, please? No, unfortunately, we are defining a function from the set A to the set B. So I do require elements to be exactly yes, this needs to map to an element of B. So I'm going to put a lizard at a 3. What's the ferocity of a seagull?
Would you pull the paper up just a smidge?
Oh,
Thank you
yep.
so much.
Yeah, ferocity of a seagull is a 7. That sounds fine. How about the ferocity of a squirrel? 8. Interesting. And the ferocity of a tiger? 2. Tigers are ferocious at size 2. Okay, so the first question is this a function that I have described? F for ferocity. Okay, I've got some confident yeses. What are the confident yeses saying? Why is this a function? Someone's got to say something. That's right, exactly. I have unique pairs. For each element of A, I have a unique pair A comma B for some element of B. Exactly. For each element in the domain, there is a unique element in the codomain. Okay. So for instance, the pairs that I would make would be like lizard 3, seagull 7, etc. Okay. First question, what is the domain? I would kind of disagree. The domain is not, I mean, this is kind of tricky questions. I'm not saying that you're incorrect, but the domain is just the set lizard, seagull, squirrel, tiger. It doesn't contain all animals, right? That's a different function. It is the set containing lizard, seagull, squirrel, tiger. Similarly, the codomain is what? The codomain is the numbers, the integers 1 through 10, because that is the possible values that this function could take. What is the range of the function f, or the image of f? Yes, exactly. The range of my ferocity function is the set containing 2, 3, 7, 8. This is a subset of the codomain, and it's tracking precisely which elements of the codomain got hit by my ferocity function. So the range is a different thing from the codomain. Not every element of the codomain needs to be in a tuple. That's right. It's possible for me to have a codomain which is larger than the range, because not every element of B needs to appear inside a tuple. Here's an example. 4 does not appear inside any tuple in this function. Yes, the codomain is 1 to 10. And what's the image of 7? Or sorry, what's the pre-image of 7 under this ferocity function? The pre-image of 7 is, I think, seagull. We put squirrel at a ferocity of 8. Sorry, but that's probably because it's impossible to read what I'm writing. Okay, so are we kind of a little more familiar or comfortable now with some of these notations and writings? Or sorry, yeah, just notations or terminology. Okay, is there anything in the pre-image of 4? That's right. Nothing maps to 4, so there's nothing in the pre-image of 4. There's no pre-image of 4 because nothing maps to 4. Okay. Any questions on this terminology? Okay, let's do another example. This will be a less fun one, but that's okay. A, B, C, D, and over here I'm gonna have, I don't know, negative numbers this time. -1, -2, -3, -4. Okay, I'm going to do a new relation, which is going to be given by the following. A is going to map to -1 and also -4. C is going to map to -2, and D is going to map to -3. This is a relation, right? Can someone list for me what the elements in the relation R are? This defines a relation, namely a subset of tuples, right? A subset of the cross product. What should be inside this relation?
A comma -1 and A
Yep.
comma negative, what was it, 4?
Yep, A comma -1's in there, A comma -4 is in there.
A -1, 2, I think it was.
C comma -2 and D comma -3, right? These are the collections of tuples that are kind of defined by this drawing that I gave, right? And this is indeed a relation because it's a subset of the Cartesian product. This is a relation. Is this a function? All right, I've got one no from Val, and another no from Naomi, and another note from a whole bunch of people now. I can't read off all your names that fast. Can someone tell me one reason why this is not a function?
Not every element in A is matched to an element, like a unique element in B.
That's right. B has no image. This is one no-no for this thing not being a function. So B has no image. I could try to repair that by sending B over to -2. But then there's another problem, which several of you have listed, is that A has 2 images. A has 2 images. So the image is not unique. This is another no-no for functions. Okay, so in order to have a function, here are 2 things that went wrong. First, B was not mapped to anything, and A was mapped to too many things. Both of these things break the fact or prevent this relation from being an honest, genuine function. Is that reasonable? Is that okay? Can sets be elements a part of the domain of a function? I'm a little unclear about what you are asking. I don't quite understand. Are you asking, can I make a set of sets over here and make a function there? And the answer to that is definitely yes. I can do this between any sets. So for instance, yeah, here's a very reasonable one. Let me do the sets 1, 2, 3, and the sets Z, and the set R, and the set 1, 2, 3, 4. And then this is going to be my set A. And I'm going to have a set B, which is going to be, my set B is going to be the positive integers greater than or equal to 0, union the symbol infinity. Okay, here are 2 sets. And then I'm going to define a function from A to B, which is called the cardinality. Now, f from A to B is going to be called the cardinality function. And what is f going to send this element, which is also a set, to? What's the cardinality of this set? How many elements are in the set 1, 2, 3? 3, thank you. How many elements are inside the set 1, 2, 3, 4? 4, good. This is a trickier question that we're not necessarily totally ready to understand, but probably you have a right guess. If I had to assess the cardinality of Z, that is the integers, would it be mapped to any positive integer, or should I map it to infinity? Here, this is a symbol called infinity. I'm not actually discussing what infinity is. I'm just saying I probably, if I'm trying to set up a function called cardinality, I probably shouldn't send the integers to any integer. Okay, so I'm going to set this to infinity, and I'm going to send R to this new symbol infinity. And this is a perfectly good function. Can someone go through and tell me why this is a function?
I think I'm kind of confused.
Okay.
What did the cardinality of the functions have to do with the fact if they're a function or not?
So this is a set. And
Oh, the whole thing is a set?
That's right. That's right.
Oh, okay, that makes more sense.
So this whole, this set A has 4 elements in it, and those elements are the set containing 1, 2, and 3, the set Z, the set R, and the set 1, 2, 3, 4. And then the set B is an infinite set, and its elements are the positive integers, including 0, and this wonky symbol, which is a sideways 8. These are the elements of this set. Most of them are numbers, one's just a symbol, but that's fine. That's still a set. Right?
Yeah,
Do
that
we
makes
agree
a
that
lot
I
more
have
sense.
2 sets? Yeah. Right, so I have 2 different sets, and then what I did with F is I assigned to each element of A unique element of B. And here I did it by just listing all of the elements of A and telling you exactly where they went. I sent the set 1, 2, 3 to 3. I set the set 1, 2, 3, 4 to 4. I sent the set Z to infinity, and I sent the set R to infinity. And this is a function because to each element of A, there is a unique element of B. Now, the only reason that I brought up cardinality is because there's like a reason why I sent this one to 3 and I sent this one to 4 and I sent this one to infinity and I sent this one to infinity. I could come up with a new function between the exact 2 same sets, which does the following. I could make a new set G from A to B, where A to B are as before, and I could let G send G of 1, 2, 3 is equal to 100. And I could set G of 1, 2, 3, 4. I could make this to be this symbol infinity, and then I could set G of Z is equal to 2, and G of R is equal to, I don't know, 0. Is this a function from A to B? Yes, this is also a function from A to B because I have assigned to each element of A a unique element of B. This is a function. Any questions here about these interesting examples of functions from one set to another set? And yes, Yutong, you had exactly the right idea. Any other questions? I feel like maybe there are questions, but no one's asking anything, so I don't know what to do.
I have a question real quick.
Yeah.
So, is it possible for like 2 different elements in A to have the same image in B? Would that still be a valid function? Or
Oh yeah, for sure, right?
Okay.
Like here, f of z went to infinity and f of r went to infinity. So for instance, here's another example of a function. A, B, C, D. Let's send all of these to -1. All these are going to -1. Is this a function?
yes,
Yes, it's a function. And why is it a function?
because each element in the domain is mapped to a single element in B, I think.
Exactly.
I think
Each
the phrasing
element,
with like a unique element in B is what gave me like a misconception of what it meant there.
right. The uniqueness means that I'm preventing A being sent to both -1 and 3. But it's fine for A to be sent to -1 and B to be sent to -1 because I still, for each element, for each x in A, I have a unique tuple, exists a unique tuple x comma B inside A cross B. Namely, here explicitly I have the tuple A comma -1, I have B comma -1, I have C comma -1, and I have D comma -1. The uniqueness says I cannot have another A comma 4. I can't have A appear twice on this list. That's what the uniqueness is getting at.
Thank you.
And I can't have B or C or D appearing more than once on this list of tuples. This is a function. Great. Thank you for that question. Any further questions? Okay. So when are two functions the same? Two functions, f and g, are the same if they share the same domain, codomain, and f of a is equal to g of a for all a inside a, their common domain. This is a definition. When are two functions equal? Alex, what was that yes for? I have missed that.
I think the last question was if it was a function.
And indeed it was a function. Yes, thank you. Okay, so here's a good question. Let's do the function f from R to R given by x maps to x squared. Namely, you take a real number and you square it. Is this the same function as g, the function from R to R greater than or equal to 0, x maps to R, x squared? No, these are not the same function. Why are they not the same function? The codomains. They must share the same codomains. It doesn't even matter if their ranges are the same, right? The ranges of these two functions are indeed the same. But when I write a function, I'm very careful with my notation. I write the domain, I write the codomain, and then I describe the function. And here, this is a different codomain. That R greater than or equal to 0 is a different codomain than R. So just from my definition of when two functions are the same, these are different functions. They're obviously very closely related because these functions share a range, right? What's the range of this function?
X to x squared.
So the range is the subset of R that gets hit by this function, right? So let me draw this function, right? X squared is your standard parabola, right?
So wouldn't it be infinity then?
So here's a question. Does 1 appear in the range of this function x maps to x squared? Namely, is there a number such that when I square it, it gives me back 1?
1.
1? Is there another one that works?
0.
0 squared will give me 0. But how about, yeah, -1?
Oh,
So
I see what you're asking.
when 1 is squared, it hits 1, and when -1 is squared, it also hits 1. So in any case, I know that 1 is hit. So 1 is in the range of this function because I can find a real number such that when I square it, I hit 1. How about 0? Is 0 in the range of this function where I square the number? Yeah, what's the preimage of 0? Yeah, when I take 0 and I square it, it's equal to 0. So in other words, 0 is hit. So 0 is inside the range. What about 4? Can I hit 4 with this function?
Yes.
Yeah, what's something that hits 4?
2 and -2.
2 maps to 2 squared, which is equal to 4. And -2 maps to -2 squared, which is also equal to 4. So something does hit 4. Actually, two things hit 4. This is a terrible drawing. Okay. So 4 is also inside the range of this function. How about, I don't know, pi? Yeah, perfect. The square root of pi will map to square root of pi squared, which is equal to pi. And also the negative square root of pi will be mapped to negative square root of pi squared, which is also equal to pi. So pi is inside the range. What about any positive number? My claim is that any positive number will appear inside the range of this function, and you can see that from the graph of the square root, because any positive number, to find what the preimage is, you draw the horizontal line through that number, and it intersects the graph in these places, and those will be the two real numbers such that when you square them, you hit this number. Okay, next question. Does -1 appear in the range of this function? Correct. -1 does not appear in the range. Can someone tell me why? The domain is all the reals, and what is the square of a real number?
It's positive.
It's always greater than or equal to 0. It could be 0, but yes, we think of them as positive numbers. Exactly. So the point is, what is the range of this function? Range of f, or image of f. What is image of f? This is a set, and it should be a subset of R. Precisely. It's going to be R greater than or equal to 0, or you could also write it as 0 to infinity inclusive. Both of these are subsets of the codomain R, right? This is getting to be a really messy page, but I'm happy with what we're discussing here. So we agree that we have found the range of this function, which is squaring. Okay, this function g is a different function because, why is it a different function again? Remind me.
Because the codomain is specifically greater than 0.
Right. I immediately know these are different functions because the codomain is different. Here the codomain is R, and here the codomain is R greater than or equal to 0. But what is the range of this function? It's the same. It's going to be R greater than or equal to 0 as a subset of R greater than or equal to 0. These two functions share absolutely everything except their codomain. They share a domain, they share a range, and they send all elements to exactly the same place, but they cannot be called the same function because they do not have the same codomain. Nonetheless, these functions are obviously very closely related, but I just want to highlight the strict requirements we have for two functions to be called the same. Okay, it is 10:11. I'm going to end class now. I know that several people had questions for me.